The first talk session is an invited talk by Tetsu Iwata, and it's my great pleasure to introduce Tetsu to you. So, okay, Tetsu Iwata got his PhD at the Tokyo Institute of Technology in 2002, and now he's now a professor at Nagoya University. He has been, many of you have known, but he has been renowned as one of the pioneers of the field of probable security world. And he developed a number of famous and useful algorithms. And the most significant one, I would say, is he's a co-designer of the OMAC published in FSE 2003, and now becomes the NIST recommended mode of operation for authentication called CMAC. And this CMAC has been adapted enormously and quite widely in numerous real products and protocols. And he's also a co-designer of the ISO standard block cipher called Clefair. Recently, he's also working on the quantum security of symmetric key algorithms. Okay, and he also received a number of awards, including the FSE 2015 and the Crypto 2019 and the Test of Time Award from the paper published at the FSE 2006 and 2007. It's incredibly good. Okay, he has contributed to the FSE and the ISL community for many years, such as by serving a lot of ISL journals and journal editors and program chairs and the steering committee as well. It's my great pleasure to him again, and as a maybe a wrong friend, both in research and friends. So please welcome Tetsu.
All right. Thank you very much for the very nice introduction. And thank you for program committee members and program chairs to invite me to give this talk here at FSE 2025. So my name is Iwata, and today I will talk about CMAC. So let's start with the developments of the early history. The starting point is the CBCMAC. This is a message authentication code based on a block cipher. And the input is broken into blocks, and we run the block cipher to obtain the tag. And it is well known that this allows a length extension attack. So if we have a tag for a 2-block input message, then you can create a tag for a 4-block input message, namely the tag for M1, M2, M1 XOR T, and M2 is T. Despite this limitation, CBCMAC was already in standards in 80s. So CBCMAC was in the standard of US and also in the international standard. There is a security proof up to the birthday bound for fixed input lengths, because for fixed input lengths, there is no length extension attack. And there are also birthday attacks. And there are various proposals of CBCMAC variants. And I just listed here a few of them: Retail MAC, Ripe MAC, eMAC, and so on. I cannot introduce them all, but let's see some of the examples of the early designs. So this is one called MACDES, designed in 1998. It uses 2 keys. The 0 panning is used here. So it can handle partial input block. And the input length is prepended at the very first of the input. And with this, it can handle variable input length messages. This is another one called EMAC. And it uses 2 keys, and we run the CBCMAC, and we encrypt the result to obtain the final tag. All the messages are padded, and this is probably secure for variable length inputs up to the birthday bound. And there is another proof by Voduni. So these developments were made to address the issues in the basic CBCMAC and its variants. So the basic CBCMAC does not cover variable length input, does not cover variable arbitrary input length. There is a birthday bound security, key length issue, the number of block cipher calls, and so on. And these only CBCMACs were designed for DES, the previous block cipher for 64-bit block and 56-bit key. And the development of AES and NIST MOO's development efforts triggered more proposals. We saw the design of XCBC, ALMAC, TMAC, OMAC in early 20s. And let's see how this works. So XCBC uses 3 keys. This is called the 3-key construction. It has 3 keys. And we just run the CBCMAC. And the idea is to pad only when necessary. So if the last block is full, we don't use the padding, and we use K prime as the mask for the last block cipher call. Otherwise, we use the padding for the last block, and we use K double prime as the mask. And with this, the number of block cipher calls is minimized, and it makes this number of block cipher calls, which is optimal. CMAC reduces the number of keys from 3 to 2. So instead of using K double prime, it replaces it with 2 times K prime. And this is OMAC. It reduces the number of keys to 1. And this L here is obtained as the encryption of 0 bits. And this L is used as the mask for the last block cipher call. So the key length is just the block cipher key, and this makes this number of block cipher calls, where one call can be executed during offline. ALMAC is a little bit different. It uses 2 keys, and it uses a random string here. The main computation is done with key K, and the last one uses K prime XORed with the random string. And the tag is R together with T. And there is another proposal by NIST. NIST actually intended to specify ALMAC as the standard. But they tweaked the scheme a little bit, and they allow to use a nonce instead of a random string. And so ALMAC has beyond the birthday bound security, but with the nonce, it drops to the birthday bound. So NIST modes of operation development started around 2000, and this is still ongoing today. And around 2002, there were 6 MAC proposals: OMAC, PMAC, ALMAC, TMAC, XCBC, and ECB. And NIST once published the early draft of NIST standard document to specify the ALMAC authentication mode. And this triggered a lot of public comments mentioning many concerns on this choice. And you can still look at this website to see public comments, and NIST eventually selected OMAC in 2005 in the standard document and named it CMAC for cipher-based MAC. So in the standard document, it says that core of the CMAC algorithm is a variation of CBCMAC that Black and Rogaway proposed and analyzed under the name of XCBC in reference 2. Iwata and Kurosawa proposed an improvement of XCBC and named the resulting algorithm OMAC in reference 6. And the OMAC1 variation efficiently reduces the key size of XCBC, and CMAC is equivalent to OMAC1. And this is how CMAC is mentioned in the standard document. And it has widely adopted in many applications. And there are more than 2,000 implementations listed in this NIST CAVP program by various vendors, including major operating systems like Windows, Android. And there are more applications that are not listed, like Bluetooth low energy devices. So IoT devices use CMAC. This global navigation satellite system also uses CMAC. Many automobiles are equipped with CMAC. So it contributed a lot to the real world applications. So let's look at how the very first security proof of CMAC goes. The goal is to show that CMAC looks like a random function. And the approach is to define this ideal CMAC in between. So here is CMAC. And if the very first message block is a 0-bit string, then this L appears here. We call that L is the encryption of 0 bits. And this L also used as the masks for the final block. And the proof has to deal with dependency. The ideal CMAC is defined in this way. It uses 6 independent random permutations. The very short message is padded and encrypted with P5. If it's n bits, then we use P6. If it is longer than this, then we use P1 for the very first one, P2 in the middle, and P3 or P4 for the last block. And it can be shown that this is close to a random function. The proof is almost to follow from the proof of EMAC. It is more secure than, it uses more randomness than EMAC, and the proof is close to the proof of EMAC. Now we define 6 permutations, Q1 through Q6 written here, from a single random permutation P. And if we can show that these 6 permutations are close to 6 independent random permutations, the proof will work, but we cannot prove such an indistinguishability. Because if apparently, if we make the same query X to the first and the second oracle, then these two will return the same output, but these two will return independent random strings. Or the query of a 0-bit string to the first one will give us L, which is used in the mask for these ones. So this is the difficulty of handling the dependency. And what I did is to introduce a random string, which is a secret key. And this is XORed at here, here, and here, and here, and here. And now we can prove that these 6 permutations are indistinguishable from 6 independent random permutations. And what I can see here, what we can see here is that ideal CMAC, based on these 6 permutations, is exactly CMAC. This P1 is replaced with this Q1. This P2 is replaced with this Q2. And we see that this random key are cancelled. As this continues until the end. And in the last block, we use P3 or P4. So this one or this one. And these random keys are also cancelled. And this shows that CMAC is close to the ideal CMAC. And we know that the ideal CMAC is close to a random function. So the very first proof went like this. We defined the ideal CMAC and Q1 through Q6 such that the ideal CMAC is close to a random function. Q1 to Q6 are close to 6 independent random permutations. And if we use these Q1 through Q6 in ideal CMAC, this gives us CMAC. So these Q1 through Q6 are essentially a tweakable block cipher, where the tweak can take 6 values. I think I didn't know the term tweakable block cipher when I wrote this proof, but from now I can see that it's a tweakable block cipher. So let's see some recent works. I will cover improving the security bound, some variations. Maybe I will have to skip some applications, and we will look at various attacks. So provable security is a strong guarantee of security, and many moves are proposed with a proof of security. And for any adversary with the specified resources, the success probability of the attack is small, regardless of the attack strategy. This is a very strong security guarantee because it covers adversaries that are not known today. And these are the examples of resources we are interested in. We are interested in the number of queries, number of maximum length of the queries, total length of the queries, and the time complexity. So Q is the number of queries, sigma is the number of blocks in all the queries, and L is the maximum block length among the queries. So assuming that this adversary makes queries where M1 has 3 blocks, M2 has 2 blocks, and M3 has 4 blocks. The number of queries, 3, has a total of 9 blocks, and the maximum length is 4 blocks. And the very first security bound was like this. Oh, yeah. This was slightly improved next year to sigma squared, and this is usually smaller than this value. And one of the sigma here is replaced by Q. So this is usually smaller than this one. And the latest result shows this bound. So the bound has been improved over the years, and this is the best known result so far. There are some variants, and let's look at this GCBC112 and CBCR. So this was the design from Nandi at FSE 2009, and this was designed to obtain the optimal number of block cipher calls. So instead of using the mask here, he used the rotation here. There are 2 versions, and the first one, the length of the padded message has to be more than 1 block. So this one cannot handle the very short input messages. GCBC2 does not have this restriction, but there is a non-trivial handling of 1 block messages. And the definition is not that simple. Here is another one called RCBC, and this reduces the memory requirements by using a 0 block at the very first block cipher call. And by doing this, we can eliminate the need to store the value of L at the cost of recomputing L every time. There are some applications, and we will look at EAX and EX prime. It's a nonce-based AEAD, and it achieves privacy and authenticity. EAX was designed to address various issues of CCM. This is a current NEST standard. CCM is not online, meaning that we need to know the input lengths in advance, and it is inefficient in handling of static associated data. And there is a trade-off between the tag length and the maximum plaintext length. So EAX combines counter mode and CMAC in the encrypt then MAC approach. So it's like a counter then CMAC. It's probably secure. And it is in the international standard. EAX prime is also a standard of ANSI, and it reduces the precomputation and memory costs of EX. This is for smart grid and included in some standards, and it was proposed to NIST for standardization. So what happens here is that we run CMAC to compute the tag for the nonce, but we use D here, where D is 2 times L. Then we use this N to compute the counter mode, and we obtain the ciphertext of the plaintext. And finally, we will compute the tag from the ciphertext. And we obtain the tag. Here we use Q here. Q is 4 times the encryption of 0 bits. And we can see that D and Q are used for the last masks, and they can be cancelled. If the nonce has 1 block, then D disappears. And this allows efficient attacks. But at the same time, it is probably secure if the input length is long enough. So EX prime is broken as a general purpose authenticated encryption, and NIST did not include this one in the standard. So let me show you about key check value. There is a standard that specifies the management of keying material used for financial services, like transactions in banking systems. And in the appendix, the key check value is defined. I will not read this, but just to make the long story short, the key check value is the most significant aspects of the encryption of 0 bits. S is 16 or 24 for a 64-bit block cipher, and this is defined only for DES and triple DES. And this is used as the ID for the key in financial services. And this is infinitely public data, as it is used for verification, so it is transmitted, sent, or stored in CLIA. So the adversary can learn this value, and this may seem as the special case of leakage of the internal state. And CMAC uses the encryption of 0 bits as the mask, and the proof does not take this into account. So the most significant aspects of the mask is known to the adversary, and so we wanted to evaluate the impact of the security. So at FSE 2014, we came up with an attack with this complexity that depends on the length of the key check value. And we could also prove that the attack is the best one. So the key check value affects the security of CMAC. But if the length of the key check value is not very large, perhaps it can be used in practice for 128-bit block ciphers. So let me talk about quantum attacks. Here is a classical model where the adversary has oracle access classically, and so it has a classical computer. In the quantum setting called Q1 model, the adversary makes queries classically, and it has a quantum computer. In the quantum model called Q2 setting, the adversary makes quantum queries and has a quantum computer. And in the quantum setting, quantum algorithm can be used, groove research can be used, and Simon's period finding algorithm can be used. So this is to solve a periodic finding problem, which says that given a function f, which is a periodic function, meaning that there exists a non-zero period s, such that f of x XOR s is equal to f of x for all x, the problem is to find the period. In the classical setting, we need exponential complexity, but in the quantum setting, can be solved efficiently. Simon's algorithm was used in the quantum attacks in the Q2 model against 3-round Faisal cipher and even Mansur cipher by Kuwakado and Mori. And a periodic function can be defined for CMAC. So the function is from n plus 1 bits to n bits, and it maps b and x into CMAC k of alpha b and x, where alpha 0 and alpha 1 are n-bit constants. So here we have alpha b in the very first block, followed by x, and this gives us the output of the function. And we can see that this is a periodic function with this period. Because if you flip b, and if you inject this difference into x, then we see that this gives us the same output. And this can be found with Simon's algorithm, and this value is sufficient for existential forgery. This came to me with a surprise. So CMAC is insecure in Q2 model. So if the adversary can make quantum queries, CMAC is not secure. But in Q1 model, CMAC maintains probable security up to the birthday bound, assuming that the block cipher is secure in Q1 model. So if we use AES and AES is secure in this model, then CMAC remains secure because the classical proof of the information theoretic setting carries over in the Q1 setting, if this assumption holds. There are more attacks and analysis, and there is analysis about multi-user security. In this setting, there are U users with U independent secret keys, and the goal is to find one forgery of at least one of the users. It was pointed out that CMAC does not have 128-bit security because with 2 to the 32 users, 2 to the 96 MAC operations are enough to break in the multi-user setting. And the recent result shows that the online security of CMAC in the multi-user model does not degrade from the single user model. So it says that CMAC achieves what what's best one can hope for. There is an analysis about committing security. This notion was first introduced for authenticated encryption schemes, but this was introduced in crypto paper for MACs. And it was proved that CMAC is not context committing. And they proposed a variant and proved its security. Not all the notions, but for some of the notions, it maintains the security. There is also a second pre-image attack against CMAC. And it was pointed out that the second pre-image attack is possible with the birthday complexity. Yes, you can do this. CMAC is not designed to have more than birthday security, so you can do this. There is an automated security proof of CMAC. So they gave the formalization verifying a concrete bounds of the security of CMAC, and they used the interactive computer-aided verification tool called EasyCrypt to prove the security of CMAC. Okay. So as a recent analysis, I'd like to introduce you the key derivation function, KDF. So a key derivation function outputs a session key or user key, K out here, from a master key K in. So K in is the master key and K out is the user key. It is defined in this NIST document, and this standard specifies key derivation functions from a PRF. There are many other constructions, but this one focuses on the construction based on a pseudorandom function. For other input values, label is a bit string that identifies the purpose of this K out. Context is a bit string containing the information related to this user key, session key, like identities of the users or nonces, something like that. And L is the bit length of the session key. And this NIST standard document defines key derivation functions based on the pseudorandom function. And there are 3 modes of counter mode, feedback mode, double pipe mode, and this one shows a counter mode. So here is the input that goes to all the PRF calls. There is a counter, which is incremented each time we call the PRF. And we concatenate the results to obtain K out of L bits. The security of KDF requires that a KDF itself is a PRF. So for random and secret K in, KDF must be a PRF. And there is another interesting security notion called the key control security. And the key control security requires that no single party can manipulate the process in such a way as to force output keying material to a pre-selected value. Okay, I should have written here, even with the knowledge of the input key K in. So in this setting, the adversary is given the secret key and tries to manipulate the output K out. So this standard defines KDF with MAC. Okay, so let's consider the case that we use a MAC as a PRF. And a MAC is built on the block cipher, 128-bit block cipher, like CMAC. And consider the case that we want to have 128-bit session key. So we want to have one block session key here. And in this case, the counter is fixed to 1. In this way, and these inputs goes to the MAC. So let me write this K as K in and T for K out. In the key control security setting, the master key K in is given to the adversary. So this is given to the adversary. And also label and L are fixed. Let's assume that these are fixed and they are not under the control of the adversary. The adversary, if the adversary outputs context such that the output T here is a pre-specified value, then the attack succeeds. And in this case, we see that the KDF is insecure in terms of key control security. So this notion is very similar to a play mesh attack with known key, where the output targets can be selected by the adversary and part of the input is fixed by the protocol. So let's assume that this MAC is CMAC, this one, where this K prime is the encryption of 0 bits times 2, and NIST specifies how these inputs are encoded into these blocks. So the input is written in this way, and let's assume that context spreads over 3 blocks. So the first part is included in M1, the middle part is M2, and the last part is in M3. And this T here, K out, is fixed to some pre-selected value by the adversary. There are 2 attacks described in the NIST standard document. They were originally proposed by the team from Amazon that used 2 blocks, but here I describe an attack with 3 blocks for simplicity. It's much simpler. So what we want to do is that all these red values are given to the adversary, and we want to come up with context 1, 2, and 3 that are consistent with all these red values. And this can be easily done. We just fix context 1 to some value, and we can compute until this point. We fix context 3 to some value. We can compute until this value, and we can compute this context 2 accordingly. So this gives us key control security attack with order 1 complexity. And NIST says that use KMAC or HMAC, or there is also a strengthened mode to use with CMAC. Okay, so let's see one more example where we want to output 2 blocks of K out. So assume that K out has 2 blocks. So maybe we want to use these keys in the key for the even Mansur cipher. So the PLF is called twice. So we call CMAC twice. And this shows the first call, where the counter is 1. And this shows the second call, where the counter is fixed to 2. Again, all these red values are fixed. This T and this T prime are also fixed. And we want to come up with context 1, 2, 3 that are consistent with everything. Can you do this? I have a burst attack on this. So what we do is to store 2 to the 64 values of the difference between y1 and y prime 1 for 2 to the 64 different values of context 1. Okay. And we also store 2 to the 64 values of the difference between x2 and x prime 2 here for 2 to the 64 different values of context 3. And we try to find a collision between the two lists. If we find a collision, we can compute context 2 as y1 XOR x2, which is the same as y prime 1 XOR x prime 2 because of this collision. And now everything is consistent. Okay. So this is a meet in the middle attack. And this is a key control security attack with 2 to the 64 complexity. And I don't have a proof, but I think this is the best attack you can do. So assume that 2 to the 64 is a big number. It may not be that big, but just assume that this is big. The question is whether this is a secure usage of CMAC. I mean, if you want to output one block K out, it is insecure. If we require the output length is 2 blocks or longer, then it takes this number of complexity. Still, I think this is an insecure usage because it is easy to compute context such that, for instance, the first K out, this one is fixed to 0 bits. I mean, we just fix this one to all 0, and we can compute context 1, 2, 3, ignoring this one. And we can compute this efficiently, as we have seen. And based on the context 1, 2, 3 derived from this part, we can compute T prime. We don't have a control over T prime, but we can nevertheless fix the fast part to all 0 efficiently. And this actually forms a weak key of Iwata cipher. If you know the input key of the Iwata cipher is fixed to 0 string, then it cannot be secure. So key control security is close to the primary security, but the target image can be selected by the adversary, and the target can be exponentially large. So this is an exponentially large target images. And this is also close to multi-target primary security. And formal security definition is missing. So there are many interesting open problems, how to formalize the security and prove relevant schemes or attack other schemes. I'm working on this with my friends, and I hope that I will publish more details soon. So, some discussions. Provable security, as I mentioned, is a strong guarantee of security, and many modes are proposed with a proof of security. Unfortunately, some provably secure schemes, even in standards, were broken, or a gap was found in the proof. And this is a very short list of the results that I was involved. There are many more cases. And there is a very interesting results regarding XCB. And there are even more. This is slides for a CISA competition. And it says that there were 33 candidates claiming provable security, and about 1/4 of the schemes were broken. I've been working on provable security for some time, so I'd like to share some of my thoughts on this. So security proofs of even standardized schemes can contain errors. Writing correct security proof is non-trivial. The problem in the proof is often subtle, but the consequence can be significant. And ideally, they should be found before standardization or widespread use. Proofs are more complex. Verifying the correct is hard, and sometimes it takes time. In case of GCM, this was designed in 2004. Problem was found in 2012 after wide standardization and widespread use. Fortunately, in this case, proofs were corrected without changing the specification. OCB2 was designed in 2004. Problem was found in 2019. It was broken. After publication of a scheme and its proof, it seems to me that proof seems to receive less scrutiny. Attack papers are read well by the community because it is worth studying. There is a possibility to improve the attack, and there is a possibility to apply the attack to other targets. Proofs often share the same basic principle, like coefficient technique, game playing technique, and they are differ in careful case analysis, which is usually customized for that scheme. And if we know the basic approach to prove a scheme, then the intensive to study a published proof might be less important, because applying the case analysis to other schemes is less likely. Of course, there are papers with novel security proofs, and I'm not saying that I'm covering everything, but I think that's what I see. So I'd like to mention that publication of a proof is not the end of the security analysis. The proof needs to be actively checked. And I think the case of CMAC went very well. There was the original security proof that was improved soon. A part of the EX paper includes the security proof of CMAC. Further improved security bound by Nanzi. There was a security proof with the key check value. There is an automated security proof. There is a further improved security bounds, and so on. So there are multiple security proofs with different proof strategy, different setting, improved security bounds. And I think now the community has good understanding about the security of CMAC. And I think it is sufficient to comfortably export this to the outside world of the crypto community. So a proof with different proof strategy, different setting, improved security bound is valuable. So how can we improve the reliability of security proofs? I don't have a clear answer. I think automated security proof is an important direction. It's a strong tool, and I think it's a promising tool. Further development is needed. So this reference verifies the proofs of these schemes. But there was an attack on OCB2. So the proof is about the simplified version or abstracted version. A tweakable block cipher is used. And the error in OCB was in the abstraction. So there are differences between simplified version and the real specification. And I think the gap has to be filled. Authors of provable security papers. I think I'm saying this to myself, maybe. A clear, readable, and verifiable proof is essential. And the first version of a proof is less likely to fall in this category. So please try to attack the proof before submission. And I think it's a good idea to ask your co-authors to attack the proof. To cryptanalysis, a proof of security is not a message to discourage you to look into the scheme. It's a starting point of a process of the security evaluation. And please do choose a provably secure scheme as a candidate of your attack targets. So I think the situation needs to be improved. I don't have an immediately effective solution, but I think it is important to note that probable security should not be taken as the end of the security evaluation. It's a starting point. So just a summary. I think CMAC has contributed to the academic community and to the real world applications. And I think I thank the support of the community, especially FSE community, to analyze and applying and using CMAC. And I hope that CMAC will remain an interesting target of your analysis. Thank you very much.
Okay, I don't remember the where the actual inventor is about inside the doubling operation in CMAC. I mean that there's a doubling.
Yeah.
And could you elaborate for a bit on the how do you develop that idea?
Thank you. So it uses 2L here and 4L here. A more natural choice would be L and 2L, like CMAC did. So the issue is that the adversary can always force the input block here to all 0. And then this value here becomes L, the mask. And if we use L for the last mask, they will cancel. And we wanted to avoid this. And this is the reason why we use 2L and 4L instead of L and 2L.
Yeah, thanks very much. Is there any other questions? Yeah.
So you mentioned about the automated tools, but so what do you think of the situation right now, like in terms of confidence in these tools compared to like handwritten proofs?
Oh, compared to handwritten proofs.
Okay. Like compared to like the classical way of doing things.
I think automated proofs are something that add confidence to the handwritten proofs. So, okay, let me for this one, they are actually analyzing CMAC itself. And I think this is very good. But for the another reference, analyzing many authenticated encryption schemes, they are only in the abstracted version. So I think the complexity of the scheme makes the analysis harder in the authenticated encryption schemes. So if more development goes and if the exact scheme can be analyzed with the automated tool, then it may replace the handwriting proof. But I think it still needs more developments for that.
Thanks.
Another question?
Thanks for your presentation. So do you think it's possible to use AI to write the security proof? Use AI to
Use AI to write the security proof. It's a very good question. Thank you for asking. And okay, it's a very difficult question. I hope this will happen. Yeah, I think that it will add confidence to the current handwriting proofs. So I hope this will happen, but I have no idea if this can happen in the future.
Yeah, because I heard this from, I mean, from a party in my lab. They said whether it's possible to write a security proof with AI-based tools. So I don't know. I just want to see your opinion. So it's okay. It's okay.
Yeah, I don't have a clear answer, but
Yeah.
I hope it will happen.
Yeah, I also hope so.
Okay.